Hello, my name is Mohamed Hassan. I'm a PhD student in the Institute of Smart Sensors in the University of Stuttgart. Today I'm presenting our paper titled a 14-channel 7 GHz VCO-Based EPR-on-a-Chip sensor with rapid scan capabilities. The presentation today is divided into several sections. We start by the motivation behind our work, followed by a review of prior art. We then discuss the changes we made to the sensor and the readout circuit. The last two sections include the measurement results, a comparison table, and a summary of our work. Conventional EPR spectrometers are bulky and expensive equipments, preventing the widespread use of EPR. Recently, CMOS voltage-controlled oscillators have been used to both excite and detect the EPR signal. The ability to sweep a wide range of frequencies allows the VCO-based EPR spectrometers to replace the power-hungry electromagnets used for field sweeps in conventional spectrometers. This enabled the implementation of battery-operated point-of-care systems. These systems used discrete components to create an off-chip PLL to control the frequency and detect the EPR signal. They also operate at 14 GHz, requiring 0.5 Tesla magnets. In our work, we aim at reducing the overall complexity of the system by integrating the PLL on chip, enabling the use of small single-sided magnets at lower fields of around 0.25 Tesla. The next section, we talk about the VCO array. Previous systems used a VCO array of 8 injection-locked VCOs to improve the sensitivity by a factor of root n, improve the sensitive volume by a factor of n, and hence improve the concentration sensitivity by a factor of n to the power of 3/2. In our work, we increased the number of VCOs in the array from 8 to 14 to counteract the reduction of sensitivity inflicted by the reduced static B0 field from 0.5 Tesla to 0.25 Tesla. To improve the concentration sensitivity of the array. Now we discuss the phase-locked loop. We used a type 2 charge pump PLL to control the VCO frequency and read out the EPR signal. The PLL has a reference frequency of 450 MHz and a bandwidth of 20 MHz. To preserve the PLL's characteristics over the whole tuning range, an active loop filter is needed. However, the amplifier in the active loop filter needs to provide very sharp current pulses with a magnitude of 1 milliampere in less than 1 nanosecond pulse width. To ease the design of such an OTA, we propose a novel charge pump scheme that uses an assistant replica charge pumps to provide the needed current pulses at the output of the OTA, hence reducing the amount of current needed to be provided by the OTA to the mere mismatch of the two charge pumps. In our measurement sections, we present both continuous wave and rapid scan EPR thanks to the integrated high bandwidth PLL on chip. All continuous wave measurements have been performed by frequency modulating the PLL reference frequency, then using a digital lock-in amplifier to detect the amplitude of the tuning voltage of the VCO array across the VCO tuning range. we report a sensitivity of 2e⁻⁹ spins per square root hertz using a crystal of PDBA with a sample volume of 9 picoliter. For rapid scan measurements, the sensor output is connected to an off-chip high-speed ADC. A linear frequency chirp is applied to the PLL reference input. Then the ADC reads the demodulated chirp from the tuning voltage, which includes the EPR signal. The baseline is then subtracted, and then the EPR signal is digitally filtered. The wiggles indicate the rapid scan regime, which is entered for repetition rates of the triangular frequency chirp greater than 200 kilohertz. The high sweep rate, which avoids saturating the sample, leads to a twofold increase in the signal amplitude. Lastly, we provide a comparison to prior art and summarize the work. The comparison table shows both better sensitive volume and concentration sensitivity of our approach. Normalized spin sensitivity is close to the state of the art that operate at higher frequencies with a lower level of integration. Our system is also implemented on 180 nanometer SOI CMOS, which is a relatively cheap technology node that allows affordable scaling of the array size, as well as operando EPR measurements in harsh environments. In this work, we have presented a VCO-based EPRoC detector incorporating a high bandwidth PLL for implicit demodulation of the EPR signals in both continuous wave and rapid scan EPR setups. The presented EPR system achieves improved concentration sensitivity and a high degree of integration. This paves the way towards low-cost portable EPR spectrometers with sensitivities sufficient for the detection of physiological concentrations of free radicals in personalized medicine. Thank you very much for your attention, and I look forward to your questions.